OK, so in this section, I'm now going to show you what the buffer overflow actually looks like when the program executes. So hopefully from the demos we've seen before, it seems reasonable to say, OK, if I overwrite the RIP with the address of shellcode, then when the program returns, it's going to go to that address, start executing code, and it finds shellcode. So if you're not totally convinced, I'm now going to walk through the entire demo using the actual x86 instructions that this code would compile to. We're going to walk through the function epilog. Those are the steps that the function takes when it returns. And we'll see that when you take these steps, it's going to cause shellcode to execute. So it's the same idea as before. I'm just really breaking it down by showing you exactly what the function epilog would do. And remember, these are the steps that we saw a couple videos ago when we walked through the steps of calling a function in x86. So here we are in the getS function. So EIP, the instruction pointer, it points at the getS function. We're calling getS. The EIP jumps into getS, and it writes a bunch of user input onto the stack. So we're going to provide the same input as before, the shellcode followed by 12 bytes of garbage, followed by the address of shellcode. And here I'm using the very first approach from earlier, where I write the shellcode at the very bottom of the name character array. So the getS function, what does it do? It takes all of the input from the user, and it writes it onto the stack. So the user provides shellcode. OK, so I write some shellcode. The user provides more shellcode. OK, so I write some more shellcode. The user provides 12 bytes of shellcode in total, so I write 12 bytes into memory. 12 bytes is 3 rows on these pictures. Then it's time to write the A's, and I'll write 12 of them. So I'll write 4, I'll write another 4, I'll write another 4. And by doing so, I've overwritten all of name, and I've actually also overwritten this value, the SFP. And remember, the SFP is what's going to go back into the EBP register. Remember, EBP tells you where the top of the stack is. So it used to point over here, and that was a reminder to ourselves to say, hey, when you're done with this vulnerable function, and when it's time to go back to main, the EBP is going to point up here. That's our little reminder to ourselves. But we've actually clobbered that out. So instead of pointing up here, where main's stack frame used to live, we overrode it with AAAA. And if you treat AAAA as an address, I don't know what's there. It's going to be address 41414141. That's the A's represented in ones and zeros. Who knows where that is? I don't know. So we now have this SFP pointing up into nothingness. Turns out doesn't affect this exploit, so not really a huge deal. More difficult exploits might involve exploiting this value, but for now, it just points off into nothingness. And that's totally OK, because what we're really after is this RIP value over here. If I look at where this RIP is currently pointing, if I follow this arrow, it's currently pointing in the code section. It says, hey, vulnerable, when you're done, please take the EIP and point it right here, because these are the instructions of main that need to execute after vulnerable returns. But the attacker in the getS function, they're going to say, actually, you know what? I'm going to overwrite this value. So instead of pointing at the instructions of main, which is where it's supposed to point, we're going to overwrite this with the value BFFFCD40. And when I do that, OK, so RIP is gone. Its old value has been overwritten, and now it has this value. And this value just happens to be the address of shellcode, like we saw earlier. So our exploit is complete. The getS function has written all of the malicious data onto the stack. And in doing so, we clobbered out the SFP to point to AAAA, whatever that address is. And we also clobbered out the RIP to point at the shellcode. So the getS function allowed the attacker to write all this stuff into memory. So now it's time for vulnerable to return. So first, we're going to return from the getS function. Remember, we're in the getS function. The attacker wrote all this stuff as part of getS. Now it's time to return from getS back into vulnerable. So here we are. We returned back into vulnerable. By the way, this moving ESP up by 4, not an important detail, but it's because I pushed one argument to the getS function. If that doesn't make sense, it's OK. The important thing is we are now back in the vulnerable function. And so now that we're in the vulnerable function and we're done, we call the getS function. That's the last thing to do in vulnerable. It's time to return. And remember, in x86, when functions return, they always execute the function epilog. Those are 3 lines of instructions that always run when a function is ready to return. And these are the instructions that clean up the stack and put everything back where it used to be, all that good stuff. So there are 3 instructions we have to run. The first thing we do is we take ESP and we drag it back up. And what that does is it basically erases the current stack frame. So right now, vulnerable has all this space to hold name, and we no longer want that. So we're going to take ESP, drag it up to where the EBP is. So it used to be down here. Now it's up here. This is the standard step you would encounter in a function epilog. So far, nothing really bad has happened. We just took ESP, we dragged it up here. You might be worried and say, OK, well, all this stuff is now in the abyss. It's below ESP. And you're right. But luckily, when we delete things from the stack, we usually don't clear out the memory. So all this stuff just happens to still be sitting here. That's fine. Also not the most important detail, but wanted to call it out in case you're worried about this stuff being below the ESP. So anyway, the first instruction of the epilog has now executed. The ESP has now moved up. And that's good. We don't want the ESP at the bottom. We want it up here so that we've cleared out the stack frame for vulnerable. But the actual attack is still sitting there. OK, so what's the next step in the epilog? The next step is we need to move EBP back where it used to be. So right now it's pointing down here at the top of the vulnerable stack frame. I want it to point somewhere else, specifically the top of the main stack frame. So I want this to go back to its original place. How do I know the original address that I stored in EBP? Well, I put that on the stack. Remember the SFP? That's the old value of EBP. So when I'm done, I should take the value in SFP, stick it back in EBP, and that's going to restore EBP to where it's supposed to be. Except this time, because the attacker messed with the stack and overwrote what used to be in SFP, I'm actually going to take AAAA and copy those bits into EBP. So EBP used to hold the address here, and we're copying AAAA into EBP. It's a register, it can hold any value it wants. Now it's holding AAAA. And where is AAA in memory? If I go to that address, what do I find? Who knows? I have no idea, you have no idea. So now EBP is also pointing at who knows where. And turns out, not really going to be a problem because we're really after the RIP. So yeah, EBP is now pointing who knows where. If you actually try to access that memory, the program would probably crash. But luckily, we're not going to access that memory because here comes the part that we really care about, the last instruction in the vulnerable function. It says ret. What does ret do? Ret says take the address on the stack, the next address on the stack, and that's the RIP, that's the address of where I should return to, and put that address in EIP. Equivalently, what that means is go to that address and start executing code. So another way of saying the ret instruction is to say, take the next value on the stack, it's going to be the RIP, go to that address, start executing code. So that's what the program's going to do. It's going to take this address, go to that address, and start executing code. So notice EIP used to be here. I will now take this address, copy its bits into EIP, and now EIP points over here in shellcode. And the instruction pointer tells us the next instructions to execute. So we are now executing instructions that the attacker wrote. And yeah, ESP moved up by 4. Not too important for this exploit, but that's something that it did. But the important thing is EIP now points at shellcode. So the next instruction that executes is going to be the attacker's malicious code. And probably what's going to happen is you get this shell that pops up, and now the attacker can type whatever malicious commands they want. And this program is compromised. Whatever this program used to be doing, it's no longer doing that stuff. It's now running a terminal for the attacker to type in their own malicious instructions. So those are the steps of the buffer overflow. Sorry, it's the exact same thing as what we saw from before, the same exploit, but we showed you how it works in the context of the function epilog that runs in x86.